Okay, so we're going to end with a couple of quick algorithms, and then we'll tie this all up in one video. Here we have the linear search algorithm. This is the linear search of the array, and basically, what you see is what you get. This is not a fancy algorithm by any means. It's if I'm looking for example, salted caramel, which is near the bottom here, I'm basically going to start at the top of my array and examine every element one at a time. Just going to loop through it or traverse the array and just examine every element one at a time. Is this salted caramel? No. Moving on. Is this salted caramel? No. Moving on. Is this salted caramel? Finally, I'm either going to land on it or I'm going to run out of options and conclude that the search term is not in the array. So looking at the code here, this is just, in this example, I'm searching for coffee, and basically just using a simple for loop to loop through the array item by item and making the comparison. Is this what I'm looking for? Yes or no? And then if I do find it, then I have a flag variable here that I'm going to set that Boolean found to true, and that'll end the loop. So that's the linear search algorithm, and we would say the linear search of an array algorithm, this one here, is in the big O of n, where n is the size of the array. And so I mean, it's pretty straightforward, or we can express it like this in the big O of n. And we would say that this algorithm executes in linear time. Now, this is not, in the very beginning of this whole discussion, we looked at a simple algorithm that also executed in linear time. But basically, what you see is what you get, and as the size of the input increases, in this case the array, then the execution time is going to increase directly proportionally to that input size. So, okay, so that's linear time. And then one thing we have not talked about is constant time. That's this yellow line down here. Let's take a look at something like that. So let's say I have this function here. It's not even a real code function. I just threw some pseudocode in here, but we have an input here is some array of a certain size. And this isEmpty function is simply going to look at, let's say that I am absolutely certain that this array is going to be populated sequentially. Okay, so if there is nothing in that very first element, then I know it's empty. Okay, because I'm certain that if there's nothing in the first element, there's nothing after that, because I'm going to populate my array sequentially. So all this function is going to do is look in that first element and see if there's something there or not. And if it's empty, we're going to return a true. Okay, or else if there is something there, we'll return a false. That's it. Okay, and so this simple little function is completely independent of the size of the array. Okay, so we would say this algorithm executes independently of the size of the array. And, so it doesn't matter if the array has 10 items in it or if it has 10,000 items in it. All I'm doing is looking at that first element and seeing if there's something there or not. I'm not looping through the whole thing like we've seen in these other algorithms. So that's an example of constant time. It's just always going to be the same amount of time because we're always just kind of doing this one action that's not dependent on the input size. So we would express that as big O of 1. It's a constant time there. And then, and you can see this is really a no-growth execution time algorithm. It's just constant time. It's always there. Always going to be the same amount of time, assuming that it's running on the same machine. Most predictable of all of the complexity classes that, these that we've been talking about. So let's sum this all up. Okay, so these are the common complexity classes, or the big O classifications that we've looked at so far. Let's take them one by one. I think just kind of have a relative understanding of these and what's good, what's bad, so to speak. So we have a little scale here. Now the first one, the best is this constant time because it's predictable and it's a no growth execution time algorithm because the performance is completely independent of the input size. Now, this is just, it's great, but it's just not realistic for anything complex like searching or sorting. So that's going to be off the table in most cases, unless you're doing something very, very simple. Now, next best thing, so to speak, is the logarithmic time. This is the blue line here. That's a slow growth execution time algorithm. We talked about this, how as the input size grows, the growth kind of flattens out. We saw that with the binary search. That's really, excluding the constant time, that's really the best, most efficient algorithm we've looked at in this entire video series. Okay, the third, it would be linear time, where you have growth directly proportional to the input size. Very, predictable. It grows in a very predictable way. And then, now this one we have not looked at yet. This would be the big O of n log n. Okay, or the big O of n log n with a base of 2. You can also write it that way. And, one thing I didn't mention, getting back to this one, which we did look at, we talked about this notation here. You might see it like this with the base of 2 in there, but, we talked about big O and how it's not precise, and so you might see it like this too without the 2. All right, so this is in the big O of log n, or, if we're going to omit the 2. So in any case, this can also be expressed in those same ways. You might see the 2, you might not see the 2. So we would just say this executes in n log n time. And as I said, we have not looked at one of these. This is the line here. You can see it's not quite as bad as the n squared that we're going to get to last, but this is there's an example of another algorithm coming up later in the book, and that would be the quicksort. So you'll look at that later. But just for now, just know that that exists, but you haven't seen an example of it just yet. And then finally, we have quadratic time, which is n squared, and we saw this is going into the stratosphere as far as execution time is concerned, and it kind of grows exponentially as the input increases. Then we get kind of this exponential growth in execution time, and you saw the nested loops do this, and with the bubble sort and the selection sort. So this is kind of like a last resort. Especially if you have large arrays, I've said this before, those should not be your go-to algorithms for sorting the contents of those arrays. So that's it, and hopefully now you have at least a better understanding of big O and how we use it to classify and compare different algorithms, some different common algorithms that we've looked at so far.